for LLaMa, who was a student of mine back then. So let's see if I can. Yeah. Okay. So yeah, just a small slide about us. So LLaMa, when he was a student of mine at the University of Wollongong. This work was done at the University of Wollongong a few months ago, and LLaMa, he approached me as he was interested in generative AI and reinforcement learning. He also received a faculty scholarship to work on this while I was a senior lecturer there. And he's currently pursuing a master's degree at the University of Technology, Sydney. And that's the exact reason why he can't be here, because he's in the middle of his exams. So for me, I recently switched to NIB, which is a health insurance company, where I'm leading a team of ML engineers. But that doesn't really cover everything that we do, because we mostly work on AI projects. So we're doing intelligent document processing for claims, but also for pre-existing condition forms. We build agentic workflows, and both for operational efficiencies, and we're currently experimenting with our customer-facing AI agent to implement some agentic workflows. We're doing some retrieval augmented generation based on the knowledge that sits in our databases, like Salesforce and such. Yeah, the team that I'm working with, we're also building an agentic AI platform. Why are we building an AI platform? Because we have approximately 300 engineers at NIB, and a lot of them use agentic coding assistants like GitHub Copilot, Claude Code, and such, and they want to use the latest models. So and they want to have those coding assistants write code for them, automatically check for coding quality and such. So that's why we're building an agentic AI platform for them. So what's the tech stack that we're using? We're using Snowflake as a data warehouse. Most of our engineers, they either program in Python or TypeScript, but we also have a few engineers that code in Ruby and Go. And in terms of the cloud environment that we use, we're on AWS mostly. We use Bedrock Agent Core for our agents, and almost all of our workloads are either deployed on AWS Fargate, which is a managed service for containerized workloads, or Lambdas, which functions. In terms of the models that we use, it's mostly the Anthropic models, called Sonnet 3.7, and we recently switched to 4. And hopefully when image capabilities become available for the Sydney region, we will be switching to Sonnet 4.5. Yeah, so that's a bit about us. Now on to the actual paper. Sorry. In Australia, Dina also just did this. In Australia, it's customary to pay your respects to the traditional owners of the land. I'm currently near Newcastle, which is the Awabakal land. So I pay my respects to the elders past and present. Okay, so the article. In order to understand what we're talking about here, I think it would be good to revisit transformer architectures just briefly on a very high level. So we have encoder-decoder models where given any input, you try to encode that into a smaller dimensional space. And then you converge, and then using a decoder, you diverge. So the models tries to expand. So and that mechanism is especially helpful for sequence-to-sequence problems, where you translate one sequence into another sequence. So obviously, one of the application areas is text translation. So from English, in this case, the Quick Brown Fox, to French, the Renard Brun Rapide. So that's encoder-decoder models, but we also have encoder-only models. So models that only have like the left part of this picture. And they're especially good at classification because they take a text, input text, and they convert into a vector of limited dimensions. So what you see here on the left is a text, and the encoder tries to classify it by creating a vector with input weights. And in this case, the class or label animal receives the highest score. Then we have decoder-only models that only use the right-hand part of this architecture, and you can instruct them. So the ChatGPT models, for instance, those are decoder-only models. So you ask them, okay, you give them an instruction or a prompt, as we call it. Tell me something about foxes, and it starts generating text. Yeah, so the type of model architecture that you use influences how the model acts. But what if models don't perform the way they should, right? There's a few ways in which you can enhance the models. The first thing we do at NIB when a model doesn't perform well, we switch it out for another model. So if Claude Sonnet 3.7 doesn't work, we'll try Claude 4, Claude Sonnet 4, or we try a GPT model. And given the same prompts and input, we're hoping that the model performs better. Now, when that doesn't work, you start changing the prompt, right? The input that you give, the instructions that you give to the model. You can change the prompt, you can change the instructions, be more specific about the context that you give, and you can give examples. So, and giving examples, that's when you're doing few shot prompting. Few shots that refers to examples of good and bad output. So yeah. Now, if that doesn't work, and you've collected all these, if you've collected input and output examples, then what you can do is also do supervised fine-tuning, because you have those label examples, right? You have the input and you have the output. So you can retrain the model. Now, the retraining is usually not something that we're looking to do, not right away, because it takes time and it takes a lot of resources, right? We don't when you want to retrain these models, when you want to fine tune these models, it usually takes a lot of computing resources, and computing resources are expensive. So one way to bypass the the heavy compute resources that you use is parameter efficient fine tuning, where you add a matrix of weights to the model instead of retraining the original model. And that reduces the computation cost by, say, 98, 99% usually. However, supervised fine-tuning doesn't always work, especially when we have large language models, right? Because large language models tend to be creative, they tend to hallucinate, right? So what we can do is align these models to human preferences. And that's when we move into a concept called reinforcement learning with human feedback, because the humans, they provide feedback on how the model is performing. So when the model provides output or multiple outputs, candidate responses, the humans can select which response is the best out of those multiple responses, and the model can use that to fine tune its weights. So how does this work? So what you see on the right-hand side is a human that sends a prompt to a pre-trained model, just your ordinary foundation model, just an LLM that you use out of the box, and that LLM generates two responses, response 1 and response 2, and then a human evaluator judges which response is the best, response 1 or response 2. Now, what we then do is we train a reward model, and using that reward model and a policy that decides how much the original model gets updated, this loop sort of makes sure that the original model, the SFT model that we show here on the right-hand side, that gets updated based on human preference. So this is a very simple example of how reinforcement learning with human feedback works. Now the problem here is that with human evaluators and for the foundation model to be updated, you need a lot of examples, right? You need a lot of feedback from the human, and humans are expensive, and retraining is expensive. So so you're suffering from scalability issues here, because it takes a lot of time, a lot of human resources. This is why we, in this paper, we considered using reinforcement learning with AI feedback, because we automate this process with, so we basically replace the human evaluator by a generative AI model. And what we tried to do as part of this this study was to compare the effect of reinforcement learning with AI feedback on different model architectures and sizes. Right, so we used two different model architectures, the encoder-decoder architecture and a decoder-only architecture to generate a summary. And we use different sizes. So we use the small model, we use the medium-sized model, and we use the large language model. What we also did was we compared it to supervised fine-tuning, just to see if reinforcement learning with AI feedback results in a performance increase. Okay, so how did we go about this? I already told you about summaries. So what we did was we downloaded a Reddit data set that includes over 3.8 million posts, and that's what you see here on the in the picture on the left hand side of the picture. We have a Reddit post, and then on the right hand side we have a summary of that Reddit post. And we use this to evaluate our setup. So we used three different models. A Google T5 model, which is an encoder-decoder model, and it only has 738 million parameters, which is relatively small nowadays. We have a LLaMa 3.2 model, and we use the 1 billion version. And we have a larger, although large is not as large as LLMs tend to be nowadays, but a larger model from Microsoft, PHY 3.5, which is also a decoder-only model. For our prompting strategy, we used the following prompt. So we didn't use any examples, so it's a zero-shot prompt, and we used detailed descriptions of what we're looking for. So we're looking for a summary that is coherent, that's accurate, and how well it covers the information in the original post. How did we train the model? We used parameter efficient fine-tuning. So basically what you do in parameter efficient fine-tuning is you have an original model, an LLM with pre-trained weights. We don't retrain those weights. Instead, we keep this model frozen, and we add an additional set of weights. And this is what the LoRa weights are. Why is it called LoRa? Low rank adaptation, because you use two matrices, and with those two matrices, you try to capture you try to capture the task at hand in a very low rank, and that can be like 1 or 2 or 4. So this is the original size of this matrix, which is D times D number of dimensions, and this matrix here is D times R, and R is a very low rank, 1, so it's D times 1 or D times 2, very low rank. And what we then do is we multiply it by R times D to get a D times D matrix that we add to these pre-trained weights. And that's how we fine tune. We took a basic reinforcement learning setup with proximal policy optimization and KL divergence, just to ensure that the model doesn't get updated too much at a time. By the way, so why we use LoRa in general? So if we only add this matrix here on the right, the matrices A and B, that saves us 98% of weights that we need to train. 98, 99, maybe even more, depending on the size of the original model. So yeah, so that reduces model training from days or weeks to minutes. Okay, so how did we evaluate? These are just your basic evaluation metrics. Rouge 1, which measures the overlap of unigrams between what you expect, right? The summary that we had in the data set, and what the model outputs. And it's the overlapping unigram. So the single words that exist both in the data set and the LLM output. So if we briefly go back, so here we have on the right, it says shifting seasonal time is no longer worth it. If the LLM outputs the word seasonal or time, then the Rouge 1 score increases. Same for the Rouge 2 score. It measures the overlap of bigrams, so 2 words. So an example would be seasonal time is two consecutive words. So if the phrase seasonal time occurs in the LLM output, then your Rouge 2 score goes up. Now Rouge L, it's the longest common subsequence. So yeah, if we briefly go back, if we have the LLM outputting no longer worth it and shifting seasonal time, then no longer worth it is 4 consecutive words. So that's the Rouge L score that's taken into account. And then we have the BERT score, which is slightly different because it doesn't measure for the exact match between the data set, the expected value, and the new value from the LLM. Now, what it does, it computes the semantic similarity between between the expected values from the data set and the output that the LLM gives. So it says more about meaning. Okay. So what are the results? This the interesting part. What we saw in all 3 models. So what you see here on the bottom, T5, LLaMa 3.2, F5 3.5. All of these 3 models, 3 model sizes, they all improved using reinforcement learning with AI feedback as opposed to just supervised fine tuning, which makes sense because we adapted to human preferences, right? What else did we see? At the start, 3.5, which was the largest model, also had the best performance from the start, and it also had a nice gain in accuracy. Also for Rouge L, it had a very good increase. What else is there to say here? Yeah, so T5, the smallest model, actually had the biggest performance increase, like relative performance increase, as opposed to the other. So this goes up more quickly than for the bigger models. So yeah, so just to summarize, 3.5, it excelled in structural coherence, with the semantic similarity. LLaMa 3.2, it had very good what we call lexical precision. So it really mentioned the words from the expected values. And what we see in general is that reinforcement learning with AI feedback improves all these metrics. And as I said, the T5 model, which was the smallest model, 738 million parameters, had the biggest gain in semantic similarity. What else is there to say? So yeah, how did this happen? Well, probably Phi 3.5 showed the best semantic similarity because it's just a bigger model. It has more capabilities. The bigger the model, generally the better it understands language. LLaMA 3.2, it was very good at matching those expected values and its output. And T5 really benefited from that additional context about what humans prefer, right? Because it's a relatively small model. It has fewer, say, language capabilities than, say, 3.5. And that's probably why it benefits from this reinforcement learning with AI feedback. Conclusions. I think what we've seen is that reinforcement learning with AI feedback improves all three types of models, also all three sizes. And what does the future hold for us? Well, the research, this research was done approximately half a year ago. So in the meantime, we had several new models launched. For instance, LLaMA 4. We have Claude Sonnet 4.5, a few others as well. So what we're going to do is see if these findings hold for the newer models as well, and also perhaps the bigger models. And just test. Do we really need reinforcement learning with AI feedback, or can we just switch out one model for a different model to see if it works better? Also, direct reinforcement learning with AI feedback may improve training efficiency, but also output quality. So if we briefly go back to this picture here, this picture, where we have the human, where we have an LLM judging the responses and then training a reward model. This is ordinary reinforcement learning with AI feedback. But if we just have one LLM that we train a reward model without judging these responses, that might help us gain a few more efficiencies as well. Yeah, that's it for today. If you have any questions,